StereoKit is for C# developers, especially those that don't have a lot of mixed reality experience. I really designed StereoKit to be very easy to learn. So I always imagine, what if I was teaching this to students? What would they think of this API? How difficult would it be for them to learn? But at the same time, it's also a very powerful API as well. So while it's easy to learn, it's also very expressive. So the idea is if you're a C# developer from enterprise or not from necessarily game development or anything like that, you can just dive into this, learn it really easily, and start getting productive really fast. So it also helps to, because of the iteration time that StereoKit has, it's very fast to just go through, try things, experiment a little bit. So it's also really good for rapid prototyping and iterating on your designs. So hopefully StereoKit is for everybody, but I focus mostly on these people who don't necessarily have experience with mixed reality before.
Hello everyone! I'm so excited to be here and present about a topic that I'm very passionate about, which is how to represent point cloud in a three-dimensional space using augmented and virtual reality. My name is Davide, I'm a senior software engineer living in London, and I've been working with these technologies since 2017, firstly with Microsoft HoloLens, and more recently with devices like MetaQuest. Let me show you the agenda for this presentation. We will start by introducing the concept of mixed reality and the metaverse, which is widely used nowadays. Then we will see how to perform telepresence using points cloud. To perform telepresence and collaboration, we will see how to capture and transmit three-dimensional points using depth cameras and mobile devices. And then we will visualize these points cloud using a virtual reality headset. And to conclude, we'll see some lessons learned in the process. Let's start by introducing mixed reality. Mixed reality is the blending of two different realities, the physical reality where we live every day, and the virtual reality artificially generated by a machine. When we blend together these two realities, we obtain the mixed reality, where we can, for instance, augment our environment with digital objects, like digital screens on the wall or digital furniture. To better analyze the possible technologies associated with mixed reality, we can refer to the physical digital reality spectrum, which was introduced originally in 1994 by Paul Milgram and Fumio Kishino. In this diagram, we can list all the possible devices and technologies associated with the digital reality and the physical reality. Headsets like MetaQuest or Pico 4 are examples of virtual reality technologies, where we needed to create a full three-dimensional representation of worlds or assets, which compare differently to physical reality devices, mainly in augmented reality technologies like HoloLens or Magic Leap, where you can see through the lenses and you can just position three-dimensional digital object in the field of view of the user. It is clear that designing these experiences is very different compared to traditional user interfaces. When working on VR projects, I found that the concept of illusions very important for designing a proper user experience. This concept was introduced by Professor Maslater in 2009, and it differentiates on three types of illusions. The place illusion, giving to the user the impression to be there. The plausibility illusion, having the environment to react to the actions of the user. And the body embodiment illusion, giving to the user a representation of his or her body. So for instance here, I have a project which is using the default Oculus Meta SDK, where you can see how a simple representation of hands is sufficient to give to the user a sense of presence and embodiment. This is another project where I illustrated how plausibility is important in this type of experiences. We see here a virtual character which is reacting to the user directly in the headset and looking at his or her eye directly. So this gives a sense of presence and immersion to the virtual reality or augmented reality experience. There are several SDK that can enable these functionalities for development. An important one is the Metapresence platform with interaction hands and voice SDKs, and with additional SDKs for movement, eye, face, and body tracking, or mixed reality capabilities like pass-through, spatial anchors, or scene understanding. This is another example of the mixed reality toolkit, a toolkit initially designed for the HoloLens devices, which enables a sort of manipulations and different interactions with the buttons or other sliders, and manipulation also in the space, similar to the one that originally were for touch devices, but this time on the space with the manipulation, rotation, and so on. All right. We have analyzed the basic principles for mixed reality experiences and the design of them. Let's see now what happens when we connect together 3D environments. The metaverse was introduced in 1992 by Neil Stephenson in the novel Snow Crash, representing an interconnected digital world where people could live and perform actions or collaborate together. This concept highlights that the integration of multiple 3D environments is complex. And as explained by Dionisio and others in 2013, the challenges include realism, ubiquity, interoperability, and scalability. Collaboration is a very relevant topic in the metaverse. Several studies have highlighted how collaboration performed with augmented and virtual reality methodologies provide participants with a greater sense of presence. In the following section, we will analyze how to perform collaboration in the metaverse, and then we will introduce how to perform telepresence using point clouds. Several solutions are already available in the marketplace for collaboration in the metaverse. They usually employ some digital representation of users called avatars, which can be represented in a digital space for performing collaboration activities. These avatars are quite high fidelity, but they are not still at the level of providing a realistic representation of the users. Some solutions worth of mentions are Meta Horizon Worlds for social experiences, Horizon Workrooms for providing collaboration in the workplace, and Microsoft Mesh for virtual collaboration and holoportation. Instead of using avatars in the metaverse, we could use a digital representation of users based on point clouds, which are points in the three-dimensional space comprising of information related to lights and colors. To better understand this concept, I took as a starting point the LiveScan 3D project by Marek Kowalski, which is a system designed for real-time three-dimensional reconstruction using Microsoft Kinect sensors and sensed depth cameras. Using this system, it's possible to stream point cloud to AR and VR devices using Kinect sensor for capturing the data and a dedicated PC to act as a server. A similar system is presented in the literature by Portescolano and others related to holoportation for virtual 3D teleportation in real time. You can see here an example of the LiveScan 3D project in action. So I just connected a Kinect V2 sensor to a PC with a LiveScan server for capturing the point cloud from the sensor and transmitted that to the different clients. You can see here as an example the camera of the Kinect transmitting an image and the depth camera transmitted with the LiveScan server. However, it was using just a Unity application for the desktop. But what about converting this Unity desktop application for a virtual reality headset like Meta Oculus Quest? So to start, I took the Oculus toolkit and I directly used this Oculus toolkit in a Unity app and visualized that directly in the virtual reality headset. You can see here a representation of the point cloud, no more in the desktop, but in a virtual reality experience. And then I took further this example by projecting the point cloud in the Oculus headset, but this time using the pass-through API for visualizing a mixed reality experience in the space. You can see here an environment with some edge projected to the furniture just for reference, and then providing a sort of transmission of point cloud for application that could be collaboration in the future. To use the pass-through API, I found the documentation for the Oculus Quest directly in the Meta SDK documentation. So I found that the pass-through API needed to be enabled using experimental features. So using ADB, it's possible to set the experimental feature as experimental enabled to 1, and needs to be enabled in the OVR manager script of the OVR camera rig in Unity. And this also requires the usage of an additional pass-through script always available from the Oculus SDK, which is available in this image. So the system just described used some Kinect sensor to transmit the points cloud to a local area network using a socket server. But what about transmitting this information over the internet and acquiring also this points cloud using a mobile device? So as a next step, I developed another prototype, this time capturing the live source through a mobile phone, an iPhone Pro Max, with the LiDAR sensor for capturing the depth camera information, and then connecting this iPhone to the internet for the live streaming of the acquired point cloud to a WebSocket streaming server that could be deployed to a public cloud infrastructure like Microsoft Azure. And then providing these functionalities and these endpoints for consumption by some virtual reality clients that could be deployed to virtual reality headsets like Meta Oculus Quest. So the scene that I used for this prototype is derived by the VR Online Office template available in the Unity Asset Store. They provide a good starting point for the testing of this prototype with the functionalities like teleportation in the environment and furniture that could also be used for collaboration activities. And you can see here in the picture an example of transmission of points cloud in real time. Let's see now more details about the depth camera capture implementation. To capture the point cloud, I use as a starting point this project by Takashi Yoshinaga called iPad LiDAR Depth Camera Sample for Unity, which is available on GitHub. This project uses the default APIs provided by ARKit and the AR Foundation toolkit provided by Unity to capture the information and project this information in raw images in the device, in this case an iPhone, but it can use also on an iPad, and images that can be traditional images or depth images with grayscale or confidence images. So the idea here is we deploy to an iPhone device an app developed with Unity 3D and making use of the AR Foundation toolkit, which is available in the Unity package manager. And once imported this package in the Unity project, we can just enable the camera capture using AR session or AR camera objects and project this information captured by the camera on a canvas which contains some raw images, in particular for the camera image, the confidence image, the grayscale image. And once visualized these images in the phone application, we can then start a visualization of the three-dimensional points using a visualizer, which is just projecting these points with some meshes in the two-dimensional screen. And then after capturing this point, transmitting these points over the network via WebSocket using a networking script. So for better analyze the implementation of the various stages of this project, let's see what happens in particular when each camera frame is captured by the mobile device. So the first step is just to update the camera image, then update the environment depth image, the confidence image. And this is done also by reprojecting the point cloud, capturing the three-dimensional data, and creating some arrays with the depth camera information. So you can see here, when we receive vertices of color from the camera in real time, we just created some arrays of using the vector3 data structure and the color data structure provided in Unity. We create some XR camera intrinsics for receiving the information about the camera related to the specific device. And then we start constructing the three-dimensional points, in particular the coordinates of the different points and the various colors associated to each coordinate. Once we have populated this array with this information, we are ready to visualize these points cloud using meshes in the Unity client application and send these sample events received by the camera containing vertices and color. So here, this part was particularly interesting because when transmitting the vertices color using serialization and deserialization with Unity, I noticed a lot of performance degradation when performing the serialization and the deserialization operation. A lot of garbage collection was going on each time a frame was processed. So to overcome this issue, I just created some byte arrays from the information about vertices color, and these byte arrays were containing all the coordinates of the points and the respecting colors for each coordinate. In this way, we had a direct transmission of binary data over the network without any serialization or deserialization that improve dramatically performance. And via the compress library, I was able also to find a reduction in packet size with optimized the transmission over the cloud. So this was the process for capturing the three-dimensional point from a camera. And let's see now more specifics about the WebSocket implementation that initially was deployed on a local area network on a local PC and then deployed to the cloud on Azure App Services. So here as a starting point, I took the WebSocket library, which is very simple to use and enable just the creation of WebSocket server using this simple syntax. You can see here an example WebSocket server running on the port 880 for local test locally. So I put some events for verifying what happens when a connection is established or a message is received. Each time that the message is received from a client, for each connected client, I just transmit the package on the packet over the network. So in this way, using a binary form of transmission in order to optimize performance. And some logs related to errors or when the connection is closed. After deploying locally this WebSocket sample, I performed the deployment directly to Azure App Services, which enable deployment on endpoints and regions near the client's location, and also good performance, and also, of course, scalabilities if the number of clients is growing in the future. All right. So after creating the first project for acquiring the point cloud using a mobile device, in particular an iPhone depth camera, the next step was to provide an environment where this point cloud could be visualized. For this purpose, I utilized a Unity 3D project with some assets from the asset store containing some office settings with some teleporting functionalities for moving the environment, so providing this locomotion in order also to not give motion sickness to the users, and at the same time enabling the visualization of this points cloud and the capabilities to see this points cloud from different points in the room. For this purpose, I used the XR interaction toolkit provided by Unity, as it is a lightweight package and it works well with all the required functionalities in terms of interaction and visualization of the 3D object. The first step was to create a Telepresence VR scene where I positioned some starting positions corresponding to the various points in the room where we wanted the user position and able to move. And then a virtual reality camera rig, a game object, a container for the different functionalities related to the virtual reality representation, and in particular the interaction provided by an XR interaction manager and the XR rig from this game object XR rig demo. You can see that the XR rig contains the traditional functionalities for the virtual reality scene, in particular a camera offset, a representation of the left and right hands or the related controllers. The point cloud visualization was instead performed using a point cloud game object containing a mesh render, and the points cloud acquisition was performed via a networking game object that had an associated script for receiving the different packets captured by the AR camera. In this example, we can see the networking associated scripts, which was a script called connect and receive events via WebSockets. This script has associated a visualizer, which is a point cloud visualizer done with the mesh render, as explained before. And here in more detail, we can see the point cloud representation and the mentioned mesh render, which consisted in simple functionalities just for receiving the vertices and the color captured by the camera and transmitted via the WebSocket over the cloud. Let's see now the code used for processing each message. So this code containing mono behavior were written in C# in this case, and processed each message by decompressing the information contained in it related to vertices and color, and storing just the last received frame in a private field for the processing by the Unity mono behavior. So for each frame, we are just processing the last received packet, and we are extracting the information related to vertices and color, and we are just updating these vertices and color in the mesh, which is the mesh render that we mentioned before for visualizing the point cloud. So this mesh render is part of the visualizer script, which is just receiving vertices a color and assigning these vertices a color to the corresponding properties of the mesh in order to visualize the point cloud. After performing this operation, we can see an example of the scene running in a MetaQuest 2 device. So we can see this office environment where the user can perform locomotion and move around, and see at the same time the live representation of the received points cloud performed using the mentioned renderer. So you can see here how the real-time visualization of points cloud is possible. The performance are quite good, but they still need to be optimized for additional functionalities, of course, for better rendering of the points cloud in the future. To summarize the project, so we have these points cloud that are captured from a mobile camera of an iPhone device. They are sent via a WebSocket server to the client using an array containing vertices and color. These are processed by a WebSocket server hosted on Azure, and each web client is connecting to this WebSocket server and then rendering these points directly in a Unity 3D scene. Let's see now some performance considerations that I found very important for getting this project running. So the first and most important consideration was related to the performance when processing each packet, each message received by the AR camera. So initially I was performing just a simple serialization of the objects received, and I noticed that the performance were very bad in the headset, kind of 10 on 20 frames per second, which is not good. It could provide, apart not for real-time experience to the user, but also motion sickness. So the problem here was related to a lot of garbage collection that was going on for when receiving each package. It was related to serialization or deserialization. I found these issues with the Unity profiler, and then I immediately concentrated on removing the serialization. I noticed that the packets could simply be sent over via WebSockets using some array instead of performing serialization and deserialization. So we are just storing the coordinates of the points, the color of the points in a float and then a byte array, and we are processing this one directly over the network. So this is quite simple. It doesn't require any serialization, deserialization, and then immediately the problems related to the performance went away. And so that's a good lesson. Do not use serialization for real-time transmission, and it could impact the garbage collection. So the other optimization was related to the maximum number of polys that can put in a scene. Fortunately, in this particular case, we didn't have too many polys, but a general consideration, we should avoid for mobile device more than 200,000 polys, and for desktop VR, more than 1 million polys. Let's say that if we need more polys, we can use, for instance, other services like Azure Remote Rendering or points cloud support with the Azure Remote Rendering that can enable visualization of big objects containing millions and millions or tens of billions of polys. The optimized garbage collection we just mentioned before, there is another option, the Unity editor. We can use an incremental garbage collector, and these options quite useful for optimize the garbage collector too. And of course, reducing the number of draw calls by combining mesh materials. Some Unity plugins are also available in the asset store. And another techniques for reducing the draw calls is using baked lights instead of real-time lights. Okay, we're approaching the ending of this presentation, but before I would like to analyze some key findings and takeaways from the project transmitting live points cloud to a virtual reality headset. So the first lesson was avoid using serialization and deserialization for real-time point cloud transmission, as we mentioned before. And in this case, usage of byte arrays can optimize the performance. And the quality of reconstructing holograms would require multiple cameras for higher fidelity. We saw that the image and the points cloud produced in the 3D space were not particularly of good fidelity. And so probably we would need additional cameras for higher fidelity of these holograms. However, interestingly, the capture of point cloud from a mobile device depth camera of an iPhone was transmissible nearly in real time with a packet size average of 900 kilobytes, so transmissible over a traditional home connection to the internet. If we require higher fidelity, we can leverage some additional cloud services like Azure Remote Rendering for providing points cloud support and then processing points cloud that have, I don't know, millions of poly. And then in this case, they can easily be visualized on devices, mobile devices like HoloLens or MetaQuest. And the general lesson for designing user experiences on virtual reality technologies use the 3 types of illusion for improving the sense of presence for the user. In this project, we didn't have a real-time audio, but this can easily be implemented using protocol like WebRTC or similar. And most importantly, I found that the collaboration performed using this type of devices, augmented virtual reality devices, introduces a greater sense of presence compared to traditional methods, and this is widely illustrated in existing literature. So to summarize what we saw today, we introduced the concept of mixed reality and the metaverse, and then we start analyzing how telepresence and collaboration is performed, firstly on the current platforms, but also how it could be performed with point cloud. Then we saw an example of transmission in real time of 3-dimensional points using a mobile device, WebSockets, and the cloud services, and how to visualize this point cloud using a virtual reality device. So before ending this presentation, we would like to leave with a phrase from Arthur C. Clarke, Profiles of the Future, that any sufficiently advanced technology is indistinguishable from magic, because this is all magic. Thank you very much. You can see here the references of the presentation. I will put my slides online. You can reach me on Twitter or via email in the details that are available now on the screen. Thank you very much and see you next time.